Hi, it's Mrs. Scarple, and this is the bulk of the lesson for Unit 2, Lesson 5, Be There or Be Square. We begin this lesson reviewing graphing quadratic functions that are in vertex form, because throughout this lesson we're going to be taking what we learned in Lessons 1 and 2, and that's the graphing, and combining it with what we've done in Lessons 3 and 4, completing the square. So let's begin with these two examples. The first example, we have y equals 2 times x plus 3 squared minus 5. First thing you want to do is identify your vertex. Remember, when it's in parentheses, this x plus 3, that means our vertex is actually going to be negative 3, and then the minus 5 that we have on the end. Our graph is going to be 3 to the left and 3 down. If we look at this equation, we see that we have a stretch by factor of 2. And because it's positive, it will be open up. Now, we need to recall our anchor values, which are 1, 4, and 9. But because we have the stretch of 2, we need to multiply each of those anchor values by 2. So we'll be using 2, 8, and 18 for our anchor values. What that means is when I move one unit horizontally, so left or right, from my vertex, I'm going to go up 2 points to get my first anchor values on my graph. When I move 2 units left or right on my vertex, I'm going to go up 8. And then if we had room for 3 units, we'd go up 18. But I don't have room on mine. And so we can go ahead and graph this parabola. Make sure that it's a curve at the bottom and not a V, a pointed V, because this is a curve, it's not a V. Now if we take a look at this next equation, we have all the same numbers, but some signs change. So for number 2, the vertex is going to be positive 3, positive 5. This time we have a reflection over the x-axis, or what we have said is open down. And we have a stretch by a factor of 2 again. Because the stretch factor is the same as before, we can still use these same anchor values, 2, 8, and 18. We just have to remember we'll be moving in a downward direction. So right 3, up 5 is our vertex. Our anchor values are 2, 8, and 18 again. Remember, because this is open down, when you go to 1 unit left or right, you're going to move 2 units down. 2 units left or right will be 8. And then if we had room for 3 units on either side of the vertex, we would graph down 18. And I don't have room on my graph based on where the axes are located. So here we have our 2 parabolas. So once again, our learning focus is to use completing the square to change the form of a quadratic equation. So the things we've done in lessons 3 and 4. Graph quadratic equations given in standard form. Now we did the graphing in lessons 1 and 2, but that graphing was when we had vertex form. And how might completing the square help us to graph these parabolas? So let's go back to Optima. Her niece works in the shop, taking orders and drawing quilt diagrams. When the shop isn't too busy, she takes out her math homework and works on it. One day she is working on graphing parabolas and notices that the equations she is working with look a lot like an order for a quilt block. For instance, Jenny is supposed to graph the equation y equals x minus 3 squared plus 4. She thinks, that's funny. That would be an order where the length of the standard square is reduced by 3, and then we add a little piece of fabric that has an area of 4. We don't usually get orders like that, but it still makes sense. I better get back to thinking about parabolas. So if we take a look at the equation that Jenny has, this y equals x minus 3 squared plus 4, we can describe the parabola that she's been assigned to graph. We can start with the vertex. As we learned in lessons 1 and 2, this is going to shift to the right because we have a minus 3 and move up 4, so our vertex will be 3, 4. We can also say that this graph will open up because it's positive in front of the binomial squared. And we can also say that there is no stretch or shrink because the a value is 1. Jenny returns to her homework, which is about graphing quadratic functions. Much to her dismay, she finds that she has been given y equals x squared minus 6x plus 9. Oh dear, thinks Jenny. I can't tell where the vertex is or identify any of the transformations of the parabola in this form. Now what am I supposed to do? Wait a minute. Is this the area of a perfect square? So if we use our work from lesson 3, building the perfect square, to answer Jenny's question, we can justify our answer as well. So if we learned in lesson 3 that if we have an x squared, we just need a single block. And we can split it up into its 4 sections, and we know we're going to have x by x. The minus 6 needs to be divided evenly between these two rectangles. So if we take 6 and divide it by 2, we have a minus 3, which would make each rectangle negative 3x. And the number of units then would be negative 3 times negative 3, which is 9. So I don't need to take any away, and I don't have any extras. So we can say that this is a perfect square. Because we can write it as y equals the binomial x minus 3 squared. So we have a square of dimensions to the sides of a square. So Jenny says, I think I figured out how to change the form of my quadratic equation so that I can graph the parabola. I'll check to see if I can make my equation a perfect square. So Jenny's equation was y equals x squared minus 6x plus 9. And we just found that we can write that as y equals x minus 3 squared. We can identify the vertex. We can see that it should move to the right 3 units, so that'll be a 3. And we aren't adding or subtracting anything, so it's going to be 3, 0. Our graph is only shifting to the right of the origin 3 units. Because my a value would be a 1, I don't have anything here, I can use the anchor values . 1, 4, and 9 to do my graphing. So if I move 1 unit to the right, I'm going to go 1 unit up. Same with the left. If I move 2 units to the right, it'll be 4 units up. Same on the left. And 3 units left or right is going to be 9 units up. So we have 3 precise points on either side of our vertex. We can draw our parabola. The next quadratic to graph from Jenny's homework is y equals x squared minus 4x plus 2. Does this expression fit the pattern for a perfect square? Why or why not? Well, if you remember from our work in lesson 3, we know this is going to be a minus 3 because half of negative 6 is a negative 3, and when we square it, we get 9. So the constant is the square of half of the middle term, or the coefficient of the middle term. Is 2 half of negative 4 squared? Half of negative 4 is negative 2. Negative 2 squared is a plus 4. So no, and we can say because 2 is not equal to negative 4 over 2 squared. So now we need to take what we've done in lessons 3 and 4 and complete the square so that we can write it in vertex form. I have a single x squared, so I'm going to start with just one block. We need to split up the negative 4 evenly on either side. So we have negative 2 and negative 2. So that'll give us a negative 2x and a negative 2x. And then our units are going to be a positive 4. But remember, we want positive 2. So since we have 4, we have to subtract 2 from our perfect square in order to have something equivalent to this expression. So our equation is y equals x minus 2 squared subtract 2. Is the equation we have written equivalent to the original equation? So we know we have an x squared. We have a total of negative 4x, and 4 units subtract 2 units is a positive 2. So yes, it is. Then we need to identify the vertex and graph the parabola. So our vertex, that's 2 to the right, so a positive 2, and 2 down is negative 2. There's our vertex. We don't have any stretch on this, so we can use the anchor points 1, 4, 9 again. So 1 unit away horizontally is 1 unit vertically. 2 units horizontally is 4 units vertically. And 3 units horizontally is 9 units vertically. And this is our parabola. Jenny had hoped that she wasn't going to need to figure out how to complete the square on an equation where there is an odd number. Of course, that was the next problem. So help Jenny to find the vertex of the parabola for this quadratic function. So unlike I did with you in lesson 4, I'm going to go ahead and just use decimals with this problem. So we have one block that we need. We have x by x for our x squared. Now, these two rectangles need to be the same size. So we've always said, well, we need to divide b by 2. So 7 divided by 2 is 3.5. And then to find our units, we have to take 3.5 times 3.5, which I believe is 10.25. I'm just going to double check with my calculator here. $12.25, so I was off. It is 12.25, not 10.25 for our units. So now we can write our equation as y equals x plus 3.5 squared, but something we do need to take a look at. We have a plus 10 and we had 12.25. So to turn this into a 10, I would need to subtract 2.25. That means I'm also going to subtract it from my perfect square, 2.25. So my vertex will be left 3.5, so that's negative 3.5, and down 2.25, so negative 2.25. Here we've got more practice, so don't worry if you had to think hard about problem 5. We're going to be doing some more. So again, we have a single x squared, so let's just make one block. And we know we have x by x. But again, we need half of negative 5. So that's going to be negative 2.5, negative 2.5. So our units are going to be 6.25, I believe. Yes, 6.25. So if we compare that with the 3, that's 3.25 more than we need. So we need to subtract 3.25. So our vertex, or our equation is, let's start there. Y equals x minus 2.5 squared minus 3.25. So the vertex is going to be 2.5 to the right, so that's positive 2.5, down 3.25, so negative 3.25. Let's take a look at example B. Again, we only need one block. We have x on each side. Now remember, if you don't see a number in front of a variable, that number is understood to be 1. So we need half of negative 1. So that's going to be negative 0.5. And when we multiply to get our units, that's going to be a positive 0.25. Now I had some students say, how can that be? Because they know 0.25 is less than 0.5 and we're multiplying two numbers. Well, you also need to think of this as we're looking for half of a half, which is 1/4 or 0.25. Now keep in mind, we need to have a negative 5 value. So we need to subtract. If I want to get negative 5, 0.25 is, to get to 0 would be a subtract 0.25. To get to negative 5 is another 5. So we need to subtract 5.25 to get that value of negative 5. So our equation, y equals x minus 0.5 squared minus 5.25. So now we can identify the vertex, and we know it's going to go to the right, so positive 0.5, and it's going to go down 5.25. Number 7. Just gets better. This time we've got a coefficient in front of x squared. So we need to help Jenny find the vertex for this one. Again, we're going to complete the square, and we can do this with 2 blocks. Mark that we have x and x for 1x squared and another x and x for 2x squared. We have a total of 1, 2, 3, 4 rectangles. So if I divide 12 by 4, that's going to be 3, and because 12 is negative, it will be negative 3. And then the units, negative 3 times negative 3 is 9. But we have 2 9s which add up to 18. 9 plus 9 is 18, and we only need 17. So we need to subtract 1. So we can write the equation y equals x minus 3, and there's 2 of them, so we need 2 times x minus 3 squared minus 1. So our vertex will be located 3 units to the right, so at 3 and 1 unit down, so negative 1. So 1, 2, 3, here's down 1. But we have a stretch by a factor of 2. So our anchor values of 1, 4, 9 each need to be multiplied by that stretch of 2. So we will, when we move 1 unit horizontally, 2 units vertically, 2 units horizontally is now 8 units vertically. 3 units horizontally is now 18 units vertically. So 1 unit horizontal is 2 vertical. 2 horizontal is now 8. And I don't have room if I were to go up 18. So here is the graph. Now, number 8, they say this one's just too cute. You might be thinking, uh-oh, what do I do if I have a half? Because we can't really make half a block, can we? So, you know how on the previous example, we had 2 boxes, and each box really has 6x. If I divided both of these by 2, I would get 1 box with 6x. So that's what we're going to do on this next one. We're going to factor out or divide by 1/2. So we're going to have 1/2 of x squared plus 4x, because we actually have, there's 4 halves that go into 2. So that's why when you divide 2 by the fraction 1/2, you'll get a 4x. We will need to find out what's going to go here so that we can complete our square properly. So let's start with a box. And I'll come back to that 1/2 in a minute, because we're going to use it to figure out if we need extras or if we need fewer. So we've got x and x. 4x is going to be split up as 2x. So plus 2 plus 2. So our units here are 4. But keep in mind, we have 1/2 of 4 is 2. So if we wanted to get a -3, we have to be looking at this as, I'm still taking all of this by 1/2. And 1/2 of 4 is 2. What would I do to 2 to get this -3? I would subtract 5. So the equation will be y equals, or actually f of x equals, excuse me, I've screwed this up on every problem in this video. The function is f of x equals 1/2 times x plus 2 squared minus 5. So we will have a vertex of -2, -5, because we're going to go 2 to the left. This is going to open up because 1/2 is positive. But we also have a shrink by a factor of 1/2. That's what that 1/2 does to this, is it would shrink the graph. We're not actually going to graph this, we were just asked to describe it. So what are our takeaways? When you're given an equation in standard form, like y equals ax squared plus bx plus c, you want to complete the square first, that's making the box, or 2 or 3, depending on what the a value is. Once you've completed the square, you want to identify the vertex, and then once you have identified the vertex, You'll plot the vertex and apply any stretch or shrink to the anchor values, which of course are 1, 4, and 9. And this is where we finished in class. I will pick up the rest of the lesson in the next video.